spent about 10 years at Cray, the computer company working in the math libraries group there, working within the guts of large scientific application codes. Joined Sandia, and then I started the Trilinos project, which you've heard some things about today, and I still lead that. I don't write a lot of software. I write software by email and by phone, so I don't type many semicolons anymore. I lead the Mentivo project, which is a mini apps project that's been used, these small codes that are used for co-design of scientific applications and future architectures. And then I'm the lead author of the high performance conjugate gradients benchmark, HPCG benchmark, that is being offered as an alternative or a complementary benchmark to the LINPACK benchmark. So that's some of my experience in math and scientific software. But what I'm going to get up and do right now to you is be an evangelist, okay? And I've been told I might be preaching to the choir. So we'll see if this is really needed. But hopefully there's some ideas that you might walk away with from tonight's conversation. So just a bit of an outline. I'm going to give some context and some definitions. And then I'm going to try to paint how the future might be different, in my opinion, how I'd like to make it different. I'm going to talk about completeness as a philosophy, and then go through some of the concepts of reproducibility, sustainability, productivity, and then try to give some practical strategies that you yourself might use to try to improve the quality of the software that you're working on. So, are we the only people who care about this? No, we're not. The National Strategic Computing Initiative has been underway for about a year now. And if you go look at the fact sheet for NSCI, productivity is mentioned right in prominently in this fact sheet. It's a very short document, and there are a couple paragraphs in it that talk about productivity. So these concepts are really important, not to just our group, but nationally and internationally. So a lot of people care about this. All right, I'm going to give you very short definitions of reproducible, productive, and sustainable. What do I mean by reproducible? That you got the real result. Not something fake, not a coincidence, but something that's real. In essence, that's what reproducibility is all about, is making sure we get something real. What is productive? You may have heard the phrase, better, faster, cheaper, pick two of the three. If you're working on a project and things aren't going well, you're behind schedule, you're not making as much progress as you thought you would, often you can change two of the three things, but not all three. Productivity is really about trying to improve the volume, better, faster, and cheaper. Taking a step back from your daily activities and trying to figure out, how can I do a better job? How can I increase the volume of those three measures as I go forward in my work? What does sustainable mean? Sustainable simply means that you have an idea in your head about how long a piece of software should last. A lot of high-performance computing codes last decades. And so if we're going to make a contribution to the repository of a software product, like pFlowTran, for example, you should have in your mind that that contribution should last the span of the life of that code, which is going to be decades. That means you just don't willy-nilly drop in a line of code, that you put some thought into what you do and you put in artifacts around it that will help that piece of code be sustainable. All right, so those are some definitions. How will the future be different? I think three major things are going to happen, and they're already starting to happen, and you can help make them happen. That's actually why I'm here. That's why I came all the way here to talk at dinner time. It says I want to evangelize you and make you part of the solution as we go forward. Okay, so what is going to happen? I think publishers are going to start demanding reproducibility of the results in your papers. Okay? This is not going on right now, with a handful of exceptions. When you publish a paper, you get all sorts of people looking through your prose, looking through your theorems, right? Looking at the line of reasoning in the text of your code, but they just blindly assume that your published results are correct. Now, not everybody does that, but you'd be surprised at how little scrutiny results get in a publication. Furthermore, they don't ask us to provide the context that produced the results. What systems did you run on? What compilers did you use? What information would be needed so that somebody else could replicate those results? We want to change that, and it is changing. The second is funding agencies. We're working with our funding agencies and to start to demand more from us in terms of evidence that we're producing high-quality software, that we're producing sustainable software, that we're educating and training the people who write our software and maintain it so that it can be sustainable. So we're starting to see that come up in content. And employers, this is the one where we're weakest perhaps in my experience, is that employers, getting our employers, whether they be universities, laboratories, or industry, industry's probably best at this, at least in mainstream software. That's why you see all these books that are out there, all of these high-profile, popular speakers. But all three types of employers, if you list those as the three major types you might go to, really could improve in their valuation of software work. You know, if you produce a high-quality piece of software and you work on that year after year after year, you should get some credit for that, right? That's not just a paper that you use to produce it, but actually by doing that. And we'd like to see that change. Why are these things really important? Well, it's because there's this kind of virtuous or bad cycle that you go through, right? These incentives, if they're there, will improve the quality of our software. If we expect high-quality software, if we get employer recognition, that provides the incentive to produce higher quality, high-performance computing software. And high-quality software gives us the ability to deliver those other things, right? And so there's this cycle that's going through. And as an evangelist in this area, I often get people to confess to me, right, saying that I would love to do a better job of my software, but I have to write this paper. I have to, satisfy this task in my proposal, or my employer doesn't value it. It doesn't go into my rank and tenure file if I do this kind of stuff. So what we're trying to do is change that. We're trying to change the incentive system so that those things are recognized. Okay, so I use the word HPC complete. I borrowed the concept from a book called Code Complete. How many have read that book? I guess we're into instant polling here. Non-Twitter style. No, oh, great book. Okay, it's a little long in the tooth, but it's a great book, right? And so I would highly encourage you to take a look through it. Actually read it cover to cover. It's a great book. Structured basic testing is covered in this book. Every time you have a logic branch in your code, that means you have another test, right? And that's just a basic principle of code coverage. But the principle behind the title of Code Complete is that it's really all about writing code. When we write software, that's what really matters. But if you're going to write the best software, there's a whole bunch of other things you need to do in order to make that the best software. That's what he means by Code Complete. So the first principle is producing software. In this setting, our first principle is doing HPC, but that means we have to do some other things in order to do the best HPC that we can. And so that's why I use that title. And we're in Illinois. Abe Lincoln grew up here, as I understand it, right? But this shows us that this preparation part is really important. And then the same thing with Dwight Eisenhower, right? Planning, right? Planning is really, really important. Even if you throw the plans away, planning is about preparing for the unknown. An emergency is something that happens that you didn't plan for. So it's the planning activity that's important, not the plan itself so much. Okay, and so let's talk then about a few of these things. So incentives to change. Why did I mention reproducibility? Well, here are some questions in mind. What is reproducibility? How can we improve it? What does this mean for you? If you read the New York Times, you may have seen this article is now about a year or so old. But there have actually been a number of articles. In fact, the science community as a whole is kind of panicked about this situation right now. We haven't in HPC had the spotlight shown on us so far, right? But our turn is coming if we don't get our act together. We're no better than the rest of the science community in the reproducibility of our results. And so there's a lot of concern about the quality and the reproducibility of our scientific results as they're being published. This article talked about a team that went and tried to reproduce a bunch of psychology results, sociology results, and how poorly, right? And there are numerous studies in other fields that are similar. And so this is the situation. This is the kind of panic mode we're in as a science community. And in fact, there have been workshops. I was at one in February, the AAAS, American Association for the Advancement of Science, a workshop on reproducible science. It was the third one, and it was about computing, computational results. ACM is very heavily involved now in trying to improve incentives for reproducibility. Conferences are getting involved in this, the PPOP conference, supercomputing. So everybody wants to improve this, improve the incentives, but so let's talk a little bit about what reproducibility is. If you sit and think long and hard about reproducibility, it's kind of a fuzzy concept. There are lots, and it's not fuzzy in the sense that we can't define it, it's just that it has lots of dimensions and lots of situations. And in fact, it's a sorry state of our field right now is that there are actually two competing taxonomies for the reproducibility terminology. There's this one, which I subscribe to simply because I've been involved with ACM, but there's another competing one, and we have to actually, over the next year or so, reconcile the differences. In fact, it's so bad that two terms mean the opposite things, depending on which taxonomy you belong to. So even our terminology is not reproducible, but we're actually working on a paper to try to, first of all, define those two, and then try to come to some conclusions about how, or a process that we can come to agreement about this. And there's strong opinions on both sides as to which one has the historic precedent to it. So it'll be an interesting conversation. I bring this one up because we've focused in on this one that I circled, which is called replicable research. And in this taxonomy, replicable simply means that someone can take your environment. If you've produced a computational result, and then someone's going to take your environment and try to use your environment to independently reproduce the results. Okay, I've used that definition because that's the definition that we've used for transactions on mathematical software. I'm the editor-in-chief for ACM Transactions on Math Software. It's one of the journals that is really serious about computation. It's about mathematical libraries, and so you'll see a lot of the libraries that were discussed here have published results and software design papers in TOMS. And when I came on to TOMS, I wanted to do something to try to improve the quality of the science that was being produced. I also worked with SciEM-CISC, Journal on Scientific Computing, and with Elsevier's Journal on Parallel and Distributed Computing. But TOMS was the one that was closest to being ready to try to take on reproducibility as a serious concern. And so we set up this replicated computational results process, and by which we have a special reviewer whose only job is to review the results in the paper. They don't have to care about whether this is a novel result. In addition to the global knowledge in mathematical software, they are simply experts in reviewing results. And in fact, often, they're better experts in knowing about all the math software that's available that they can inform the authors about things the authors didn't know about. So it's a very interesting dynamic. So we've been at this a few years now. It's optional. We'd like to make it a requirement. We'd like to move that way quickly. The standard review assignment doesn't change. Instead, we have this special reviewer whose job is just to review the results. And in the end, replication is a one-time, one-person event. So we're not saying that these results are reproducible indefinitely. That's a different concern, far more ambitious. We're just saying that one person at one time was able to get the same results as the author did using their environment. It's a very small bar in a certain way to get over, but it's amazing how impactful that is to upstream behavior. Getting the authors to do things, getting them to plan for that activity, right? That's what's interesting to us. And so we've been at this for quite a while. We use independent replication. There are three basic approaches. I won't go into detail. We haven't tested this yet, but if you're, let's say you're running on Titan, right, at Oak Ridge, right, and you're the only, you have this allocation. There's no reviewer that can even necessarily get to that. But if you want to apply for this replicated computational results badge, you actually get a badge on your paper now. You have to plan ahead. You have to create artifacts that will help convince the reviewer that your results are reliable, that they would be replicable if they could get. So we all allow this alternative to actually having them do it. We're trying to be practical about how we do this. So a big picture of TOMS is we want to improve science. The quality of our prose is good. We have this habit of creating good content. People review our paragraphs, make sure we're saying something clearly and forcefully, but we don't have as good a practice with the results, and we're trying to change that. And as evidence of that, The second author we worked with on this for TOMS wrote this note to me saying that, thank you for taking time to consider our paper for your journal. In the bold text is, to make this easier, we have preserved the exact copy of the code that we used. That's exactly the kind of upstream behavior change that we want to see. It gives the authors incentives to do something they might not otherwise do. Right? Even the best author might not take the time to do that because they have other things to do, and they're not getting rewarded for it. Okay, what's the status of this? TOMAX, Transactions on Modeling and Computer Simulation, has adopted the TOMS RCR process, really as is, with success. And ACM itself has built a workflow into its Manuscript Central website to support us in this. And then ACM has created badging for this, results reviewed, results replicated, badging. And so we're making good progress. PPOP and other conferences are using artifact evaluation. Supercomputing is gradually introducing reproducibility as an optional thing on the way to requirements for technical papers. I'll be on the one of the co-chairs of the ACM of the Supercomputing 17 technical program, and my focus will be on the reproducibility efforts for SC17. Same thing with AAAS. There's a science paper that will be coming out soon on reproducibility enhancement principles. So there's a lot of activity in this area. It's an important area. You'll want to track it. Okay, so what's the message to this audience? Be ready. Someone is going to review your results. Okay? And I'm guessing that may not be so scary for some of you. You seem to all be more savvy than maybe my generation was when I was your age. But be ready. That's the kind of thing that's going to happen. All right, what's another one? We talked about software quality requirements. Another way to incentivize high quality, high performance computing software. So we started some efforts with the DOE Biological Environmental Research Office and the OSCAR office to try to put language into a call for proposals that would ask the authors to tell us about their software environments. How do you produce software? How do you manage your source code? How do you track issues? How do you do your documentation? These kinds of questions. We weren't saying that they had to do it a certain way, but it's a request for information that allows us to build a foundation of understanding of how they do it, with the next phase being to try to set a norm that would raise the bar, get people to move a little bit further in their efforts. These are some of the things that were put into the call for proposals. We anticipate this to hopefully get into insight calls at some point, we hope. And again, to get information and raise the bar for improving incentives for high quality software. Why is high quality and sustainable software important? I just brought a simple example. We got a pull request. Many of you know, I heard you know about pull requests, right? On GitHub. How many of you know about that? I want to see if oh great, excellent. So we got this pull request for our iterative solver package Balos from a contributor, okay? So great, wonderful, they're exposing a new feature, it's very useful. But what do we have to have confidence in if we are going to accept this? Our testing environment, right? If you're going to take somebody else's code, in addition to making sure that they produce the proper documentation and artifacts, that everything that you'd want from a complete commit, in addition, you need to be able to confidently say that what you're bringing in from outside will not disrupt your code. And the only way to do that is to have good testing. And in fact, again, the message to you is write tests now. Did anybody talk to you about test-driven development? Okay, who knows what test-driven development is? Okay, a few of you. Basic ideas, write your tests first, write them to fail, write your software, your source code, and progressively make those tests pass. The reason that's more valuable than just writing tests first, it's also about debugging your design. If you write your tests first, you actually get some better sense of the design of your software, and I guarantee you that the design will change if you write the tests first rather than wait till the end to write them. The other reason is that a lot of people will write the functionality and then they'll run out of time to write the tests. And then you won't have tests. And then 5 years later, when you want to take a pull request, you won't be able to confidently do that. That's the main reason. Okay, let's talk about employers and productivity and sustainability. Okay, this is a big to-do right now, right? We haven't got a lot of initiatives. We're trying. We're trying within the Department of Energy to get our program managers and, to value more greatly methodologies research so that we can start to understand how our field of high-performance computing, computational science and engineering can benefit from the large volume of literature and experience in what I'll call the mainstream software engineering community. We can't just blindly adopt it. We can't just slap it onto what we're doing. Actually, I've been in, over decades, I've been in experiences where people have tried to slap commercial software engineering techniques onto scientific software, and it's a disaster. It doesn't work. They have to instead understand our community and adapt it, tune it for our purposes. And so we need to do that. We need to have some research efforts in order to make that happen. And this is where I want you to participate, okay? What are some things that you can do? Cite software, help us out there, right? Cite software. Promote with your management, whoever it is, better software practices. And evangelize for more attention to software quality. Evaluate when you ask to review something, scrutinize the results. Look and see if there's enough information about the computing environment that you could actually have a prayer of trying to produce those same results. You can put that into your review, whether the editor asks for it or not. And then promote the need for software methodologies research. Okay, so why are we different? Well, we're not as unique as we think we are, okay? First of all, you have to admit to that, right? But we are unique in some ways. It takes a PhD plus a few years or a bunch of years of experience in order to be a software developer in our community. The results from one run of your code could actually dramatically change the requirements for the next version of the code. Those are two things, okay? What is something else? If you look at agile methodologies, there's often this sense of interchangeability. You can have several people who could pick up and do the next task on your Conbond board, which I'll mention briefly a little bit. Okay, that's not true in our community very often, right? There's usually one person who's really good at writing a particular piece of software. They are the only person who has that background. Those are just a few examples of how our community of developers is probably different than what you would find in more mainstream software engineering and development. Okay. All right, so let's talk now a little bit about some high-quality software challenges and practices. Okay, first of all, let's talk about the challenges. Okay, this is a nice little chart of this book, Code Complete, that I just showed you the cover of. Okay, it talks about 8 quality attributes of software. And then it shows how they interact with each other. For example, if I pursue correctness, well, it should improve correctness. That's a good thing, right? But it also would tend to improve efficiency, reliability, accuracy, and maybe have a negative impact on robustness, okay? Let's look then at the quality of efficiency, right? The software quality called efficiency, which is closest to high-performance computing. What's its impact on other quality metrics? Okay, well, it's positive for itself. That's a good thing, right? But look at all of the negatives. Look at, by pursuing high-performance computing, you will have, on average, a tendency to reduce the impact or have a negative impact on other software qualities. What does it say? Don't do HPC? No, no, no. It doesn't say that. Don't leave the room. But what it does mean is that we have to be a lot more careful, perhaps, than other industries when we talk about paying attention to the quality of our software. Okay, so that's one thing about HPC. All right, what else? Teaming. Okay, there's this great quote from Fred Brooks, who wrote The Mythical Man Month, and a bunch of other books as well in software. But he talks about a scientist builds in order to learn, and an engineer builds learns in order to build, right? And so the problem is that we have a lot of scientists who do barely sufficient building, right? Their software is barely hanging together all the time. And then we have engineers who could probably do a better job, who don't learn enough before they go off and try to build something, okay? So that's a recipe for disaster in a lot of cases, but what if you could team, right? What if you think of yourself as more a scientist person? What about teaming with an engineer? Vice versa, the other way around. So teaming is really important. What are other things that are important? Best practices. Often we're trying to write software, we're trying to produce it. We don't have a lot of time to go off and take 2 weeks and spend it out in rural Illinois. Oh, but some of you do. Okay. Anyway, but often as we move along and do our work, we actually have maybe 15 minutes or an hour where we could try to improve things. So this notion of best practices is really helpful to little by little improve the quality of our work. And the Ideas Project, I think you've heard something about, has produced a collection of what we call what is and how to documents that are these small bite-sized pieces. We're not the only source of these, but this is a really nice way to try to improve your skills as a software engineer, a software developer, is to look at bite-sized opportunities, on-demand courses, little things like that where you can little by little learn something. Okay, one more area, and I'd like to emphasize the notion of continual improvement. Always try to get better. Always try to improve what you're doing. If you're poor at something, get a little bit better. If you're good at something, get even better. And I'm going to use the notion of issue tracking. Okay, so let's say you do issue tracking right now, and you don't do anything. You just remember it. Well, create a little to-do.txt file. Or actually, no, write it on a notepad first. Sorry, that's the first step. If you do the notepad, make a little to-do.txt file, put it on your computer desktop. If you do that, move that file into the root directory of your repository so you can share it with other people. Little by little, right? And if you're already really good, then start using a web-based tool like Jira and do Conbond or Scrum, right? Always try to improve on what you're doing. Get better at it, okay? And I will mention Conbond just because I really like Conbond. I think I've sold many licenses already of Trello, which is a nice tool. I use it for personal Conbond, which is, if you want to chat afterwards, we can. Conbond is this technique for managing workflows. And the main focal point is what's called the work in progress or the in progress column. And the contract that you have if you practice Conbond is you don't work on anything unless it's in your in progress column. And you cannot put something in your in progress column once it's reached its maximum fill level until you've retired something from it. Okay, so Conbond is this workflow management principle developed by the Japanese auto industry many, many years ago. The basic genius behind it is that you're supposed to work on what's in front of you and get it done. And you're not supposed to do anything else until you get it done. And all work that comes into you doesn't get to you until you're ready to take it. Now, what happened in the auto industry is actually created this huge backlog. One team in the midstream of this whole workflow decided we're going to practice this process where we're only going to work on what is in front of us right now, and we're not going to accept any parts that aren't needed for us right now. And so it created a whole backlog in the workflow, right? It was a very interesting social experiment as well. So what it does is it changes your workflow from being something pushed onto you to something you pull. And so Conbond is about pulling work. You only take something on when you're actually ready to work on it and ready to do a good job on it. It's very interesting how the dynamics of Conbond will change your whole workflow and your whole emphasis on work in general. We use Conbond. We've been experimenting it on the Ideas Project. We also use it on the Trilinos project. We're ramping up, trying to get a feel for how this can work. It's really enjoyable. I like it. There's all sorts of really cool things you can do with it. Okay, so what's the message? Okay, HPC software is particularly susceptible to quality challenges. Scientists and engineers can complement each other and seek bite-sized practices to improve things day in and day out. Embrace continual process improvement. I showed you the example with issue tracking. HPC is not complete without better reproducibility, sustainability, and productivity. I hope I've convinced you of that you can't just go off and write high-performance computing software. You have to learn some other skills to be really good at it, right? And you have to invest in that on a regular basis. Software engineering is important for HPC because of this negative impact on other quality. You try to improve incrementally by teaming, best practices, personal bests. One thing I think is really important is that you don't want to obsess about this kind of stuff, okay? You don't want to obsess because high quality, low value software is not a good outcome, right? you really do want to be an expert in your particular area or software development, in your particular area of algorithms or computer modeling and simulation. You can't give up on that. If you spend too much time focusing on quality and then you lose your edge in your science or domain, that's not a good thing, right? So we have to be careful how we do this. Remember, Code Complete is about code. It's doing everything to produce the best quality code. HPC Complete is about doing everything to make high-performance computing the very best it can be. All right, and then hopefully I have argued effectively to you about changes that we're going to see in publishers, funders, and employers. I love you if you are part of that. And I also want you to consider an attitude that this is not bothersome, right? Having your publisher expect more from you, or your funding agency or your employer expect higher quality software is not a bad thing, right? In fact, you can be part of the proactive solution. You can be a part of the community that is going to shape what these concepts mean, and that's what I would love to see from this audience. Okay, final thoughts. So if you're a Canadian engineer, when you graduate, you get this iron ring, right? And this is a poem that's recited as part of that from Rudyard Kipling, right? There's a myth going around that this is part of a bridge that failed, that the iron rings are. That's not true. It's a good story, but it's not true. I would love to see us have this kind of personal commitment, because there are all these programmatic ways that we can improve quality. But unless we get at each individual and how they, day after day, do their work, really we're not going to make as much progress. So there has to be this individual commitment to the quality of the work we're going to do. And so for the Trilinos team, I was trying to figure out what can I do to get across this point, that I really like each person, when they sit down at their desk, to take this message seriously. And so I made up a bunch of refrigerator shelf magnets, okay? And I have this little checklist. And I want each person on the Trilinos project who's going to sit down and work on something related to Trilinos to look at this mental checklist. Is the work traceable? Traceable means, can you trace it back to some specific requirement or derived requirement from your user, client, the person who's paying for it, is going to use the software? Check. Is it in progress? This is the Conbond principle. In other words, did you plan to do this work? Or did someone just call you on the phone and all of a sudden you're going off and doing something you had no idea you were going to do that day? Bad idea. Okay, don't do that. Then the third is sustainable. Are you putting the investment into what you're doing that it will sustain through the lifetime that you expect? And then the fourth is improved. Are you doing a better job than you did a few months ago? Have you done something to make yourself a better developer? Okay, so those are the checklist items that I want. And I would ask you and encourage you to consider them as well. And in fact, I have two things for you. From across the Atlantic, I have some stickers from the Software Sustainability Institute. These are our friends in the United Kingdom who are very far along in their thinking and maturity about scientific software. And so if you want a sticker, it says better software, better research, you may have one of these. I would also love to see, I think I have enough for all of you, to actually have one of these little, so if you have a magnetic shelf or a refrigerator, this sticks right on it, right? Okay, so put it by your screen, and then when you sit down to do your work, go through this little mental checklist, okay? And I really would appreciate if you take it, because TSA actually went through my bag when I came here, because this is dense and black on their screen. Okay, so, and you won't get, if you have just one or a few, I'm sure it won't matter. I've traveled with a few of these and they never check me. It's just this big handful of them, okay? So help me out by taking one, okay? All right, and I'll stop, and if you have any questions or comments, I'll take them. Thank you. Oh, yeah, great question. Actually, there was a 1.0, right? I versioned these, right? Hey, I have to practice what I preach, or try to at least. So 1.0 was a printing error. I had to throw the whole batch away. 1.1 was similar to this, except it didn't have the QR code. And so the QR code will actually bring you to a site that explains what the concept and the principles behind it. So that's 1.2. And actually, I'm going to do 1.3 is going to have a little bit clearer. There's a little kind of fuzziness to the QR code. I have to do a better job of creating the binary for that. So thank you. Yeah, you can pass those along. Take one and pass them along. Okay. Other questions or comments?
So I have a question about reproducibility. So I mean, I know that many research groups start for CPU time. So if I burn 100 million CPU hours and publish my result, who do you think should be responsible for the other 100 million CPU hours that are needed to reproduce it? And,
okay.
and is it really?
Great question. Yeah, great question.
Okay.
Right, okay. It's all a matter of what level of risk you're willing to accept, right? If you take that 100 million hours and you produce a result, but you have not invested in making sure that you got the right answer, right? Then that could be 100 million hours totally wasted, right? So maybe you spend 70 million hours doing the forward result and 30 million looking at reproducibility, making sure you get a balance. Maybe it's 80-20. But some fraction of that time should be spent reducing the risk that the results as you got were totally wrong. That's how I would try to look at it.
If I write in my application that I'm going to spend like 25% of this time, I don't know, making sure that my results are reproducible, would it be likely to be granted?
It depends on your it depends on your funding agency, and so that's why I want your help, right? I want all of us together as a community to raise the awareness of the importance of this, that the quality of the results that we produce require some effort beyond just producing the initial results. But your question is exactly right. Yeah, great point. Thank you.
One thing I will add to that, right, from a facility perspective, right, I need to believe, right, that the science that comes out of my machine is not going to be thrown out 2 years from now, right? That is very bad for whoever was leading the science that gets thrown out, but it's also really bad for the computing facility. So while it is not every single place where you can get compute hours, computing facilities are going to look very, very favorably on that, and generally do. It is our feet in the fire as well when it comes to that.
So not every journal supports you in publishing like accompanying things. What could, for example, be the input parameters I have, and so on. Yeah. What kind of alternative possibilities do I have to publish these things which are needed for reproducibility?
Yeah.
I'm sorry.
No.
Along with my research, because there is the chance that I won't be around in 2 years, and that the code won't be around in 2 years.
Yeah. A lot of it is a culture change, right? So the initial, this is why in changing the incentive systems are very important. It is very important, because if we don't change the incentive system for publications, that publishers themselves demand these artifacts that you just described, so that 2 years from now, and maybe 2 years from now, we really won't care that it's totally reproduced or reproducible at that point. It might be that we just want to make sure that the result was solid when it was published, right? There are various levels of reproducibility, but it really is about culture change. Please, yeah. Catherine?
This is now the long-term perspective. Do I have a possibility at the moment? In 2 years' time, I might not be a PhD student anymore, but might be in industry, and then I simply, I don't know whether I would care about the results.
So let's say you published in ACM transactions on Math Software or Tomax, right? You would get a badge on your paper that's unique, because not everybody gets that. And that meant that you put in the effort that it would take to make that paper more reproducible than previous ones. And so the investment would be paying off for you in that particular setting. That's about all I can say at this point. It's a work in progress.
Can you comment on technologies like Docker, Shifter, and Singularity and the role that you think they have in these initiatives?
Oh, yeah. So I'm a big fan of Docker and Shifter, too. I didn't recognize the third one you said. What was the third one?
Singularity. It's a relatively new project coming out of LBL, but it's in a similar vein.
Okay, fine. Okay, I'm a great fan of Docker. I think, and I foresee Docker as providing us with the ability to create brand new workflows with very low barriers. You know, if you have an image that you can download and launch as a container, the barrier to using a complicated piece of software goes way, way down. And now you can start to compose these pieces together to create workflows in a scripted mode with almost no effort on your part other than the script. It's great. We've been exploring this with Trilinos. We now deliver our tutorial, a web-based tutorial using Docker. I've been exploring it in my teaching setting as a scientist in residence at St. John's University because a lot of my students don't have LaTeX. It's the first time they've seen it. And so they can just simply grab a Docker image containing LaTeX and have it on their system instantly, right? So you can create whole workflows. So I really like containers a lot.
If my understanding is correct, replication means you need to use exactly the same tools and doing exactly the same research, right? So does that mean we have to force everybody open source their code?
No. So the question is, do you have to, if someone else is going to replicate your results, they're going to have access to your software stack and your input parameters, and they're going to run your code. Does that mean you have to be open source? Open source certainly makes that possible, but it's not required. All that simply means is that one unique individual, that reviewer, has to be able to get access, and only for the time of the review. And so that's the only kind of brief window of time and singular person that has to have access. So that's a much lower bar. Great question, though, yeah.
One last one.
I'm not sure if this is the right question for you, but it seems to me like reproducibility is not unique to HPC communities.
Not at all.
It's a science research problem.
It's first and foremost a science problem, yes.
Right. So from simply looking at the experimental aspect of things where they have these huge experimental facilities such as APS at Argonne, I mean, how have they been handling reproducibility, and can we learn from them?
That's a great question. Yeah, so I actually asked the same question several years ago, and some of my colleagues who are experimentalists, and they said, well, it's not that great. I'm not sure we can teach you all that much. That was the response I get. Now, maybe I asked the wrong group. They also said to me that, and in fact it's been getting worse, as they have been introducing computing into their experimental environments, they've been adopting the same sloppy practices that we have already had traditionally in the computing field. So not only is our bad behavior impacting computing, our own simulation, modeling and simulation, but we're actually having a negative impact on the experimental side because they're adopting some of our same sloppy practices. So I don't know. My sampling was very small, but it's a great question, and it would be an interesting thing to explore more deeply, right? To see if we can learn from the experimentalists who have been at this a lot longer than we have been. Yeah, great question. Thank you.